Okay, so in the last lecture, I have discussed about the. I hope that you are able to see the board now. If you are not seeing, then you can say. So in the last lecture session, we have talked about the ideal block cipher case. Block cipher. We have also discussed and talked about the uh, basic principle, basic things we can say, basic things about this ideal block cipher, and we also discussed about the disadvantages, or in place of disadvantages, I must use a word that is uh, we can say the drawbacks, or even we can say the limitations. Limitation is the correct word, limitations, because in ideal block cipher we required a huge number of key for n block pair. We have seen that we require n block pair of plain text. We require n cross 2 to the power n bit size key length. So it is very huge thing. So that's why uh, we required some kind of the intelligent or the smart block cipher technique. So in this regard, we talked about the we now we will discuss that okay, so we will discuss now the classical feastal structure, and in this classical feastal structure, as you can see here, so for explaining this thing, I'm just putting the glass board here, and this is the glass board. Now I can write something. So this is the basic structure for the block cipher technique, and when we use this kind of the technique, then we can surely say that the key size we can reduce, and the sufficient amount of randomness and diffusion, confusion things, permutation things, substitution things uh, we can introduce here. Here we consider 2W bits. So 2W bits, whatever the bits we are consider, say 64 bits, then we will make the two halves of 32 bits, something like this, and we will do all the calculation on these two halves. In first round there is XORing. It is nothing but the round function case, and left side, right side, so left half is L0 first round, R0 is the second half, and then we will give this half block of data to the XOR, and then the each function, say round function, is having the individual key and something like this, and then when we will pass this result to the XORing case and XORing with the left half of the bits, then we will pass to the right side of the next round, and the right side of the previous round will pass to the left side of the next round, and something like this. Or in this fashion we will generate the ciphertext at the end, and after generating the ciphertext, okay, then after generating the ciphertext, we will see that this is the decryption process, and in decryption process we will do the same thing, just use the key in reverse ordering. As I told, as we have seen that at the end in encryption process there is the ciphertext at the end. Now in decryption process the ciphertext will be the input in the decryption process again, and again we divide into two halves, left half and the right half of the data bits, and the same process we will do here, but the key, the sub keys that we are using here, like K16 we will use here if we are using the 16 rounds, because generally the 16 rounds we prefer. So if 16 rounds we are considering, so in first round of decryption we will use 16th key. Similarly in second round we will use 15th key, and similarly at the last round of the decryption process we will use the first key, something like this. Otherwise the same process we will do in a reverse order. So this is the ciphertext, basically uh, ciphertext, or we can say uh, the fetal structure. And okay, no one is there, so it is okay. So I have to tell this theorem again, and I will repeat this in the next lecture session. So I'm